My presentation is on a supervised heuristic for a balanced approach to regionalization. So I'd like to motivate this from two angles to start. The first being functional regions. So these are regions that are clustered around simply a function or some sort of similarity. So you could be clustering based on how similar median income is in a bunch of areas, for example. At their core, these are a very easy concept to come up with in qualitative literature, but in the quantitative side, they can be very, very hard to draw. And many papers simply define their own optimization problem and then solve it. So it raises a sort of epistemic question about what optimization setup is correct. On the other side, we want to think about just sort of a very data, like bottom-up direction, right? So have you ever been in this situation where you found administrative data at very high resolution, low level units, but you don't know if those units are actually meaningful for the phenomenon you want to observe? So oftentimes when analysts are faced with this, they want to aggregate that up to another scale, a lower resolution scale, but it's often unclear what that scale should be. So enter our methodology. It's a sort of simple for-loop optimization process. We just set down a number of candidate clusterings for whatever problem we're considering, aggregate the spatial units and data, fit a spatial model to these units, record this error and average unit area, and then apply a heuristic that we've developed using the model error and average area. And in this way, we have attempted to devise a heuristic that uses the model's information along with demographic data or data that is simply endogenous to the spatial units in order to define a clustering that more accurately fits whatever phenomenon the analyst is trying to observe. So let's dig into this a bit more. We used an assortment of algorithms to actually perform the regionalization. According to the classification presented in Duque et al. 2007, two of these were adapted hierarchical clustering algorithms. So these lay out a minimum spanning tree across all of the clusters or all the spatial units at the very base level. And in the ward setting, you connect units based on how similar they are. And at a certain point, you stop. And whatever is connected, you've sort of formed blobs, and those are your clusters. On the scatter side, you lay out the minimum spanning tree to start, and you break off the least similar edges. And once you've broken off enough, you have a number of clusters that you want. And then the last one that we tested as well was region k-means. And this is the classical k-means clustering algorithm, just with an added spatial connectivity constraint that makes sure that we actually keep the points that are spatially contiguous together. So the real brunt of my presentation is this. Our objective is to choose a number of clusters that maximizes the goodness of fit for whatever spatial model you're using. Here we used a spatial interaction model for human movement between origins and destinations. And we want to simultaneously minimize the amount of regionalization that we're performing, because more regionalization means more information is lost. And we want to preserve as much data quality that we had from whatever high resolution data we started with. So to that end, we devised k-crit. And k-crit is this critical number of clusters. It's the minimum cluster in whatever clustering domain or whatever optimization domain we've considered. That is the minimum sum of, that produces the minimum sum of the normalized model error plus the normalized unit area. And so these are just normalizing constants. So some assumptions on this heuristic. First, we assume that the average unit area is non-decreasing. And this makes sense. So as you increase the number of clusters, we expect that the regionalization algorithm will produce more clusters. And more clusters means smaller clusters. So hence, as you increase the number of clusters, the unit area decreases. Or sorry, other way around. So then we also expect that on the other hand, the model error is well balanced. So we want it to be non-increasing, so sort of the opposite curve. And I'll show a picture of this in a moment. But it's not required, and that's sort of what we'll, I want to bring that up later as sort of a connection to the modifiable areal unit problem. And then finally, we assume that the optimization domain omega is nice. So this will be, in general, a subset of the positive integers because those are the only acceptable number of clusters. You can't have a half of a cluster created. And this allows us to do sort of the brute force for loop, just cycling through it, as I described earlier. And so this is really, I think this is probably where it'll come out together. So our average unit area decreases as you increase the number of clusters because you have more clusters, you have less area in each cluster. And the model error often increases with the number of clusters because as you increase the number of clusters, you get more and more potential noise in the problem. So we normalize these two so that the terms are on the same scale, and then minimize the sum simultaneously. And because of the curve shapes, if you minimize just one or the other, it would produce a very biased. It would not minimize. It would only minimize one or the other. It wouldn't minimize both. So the simultaneous minimization helps to sort of pick the best in some sense. And this is why we call it a heuristic. It's not optimal. We have no proofs of optimality for this. So to check out how this actually works, we did some experiments with California origin-destination flows and fit a spatial interaction model to estimate how these flows worked using the US Census American Community Survey for county and tract level attributes. And we chose to balance, so in terms of the balance between realistic simulation versus prototyping, we chose to prototype this and stick just to California for our scope. And so here are these heuristic curves. These are the summed curves, like I described earlier, of the two normalized terms. And the dots indicate the minimum. So this is sort of what I was saying, is that the model error isn't exactly just strictly increasing. It's sort of got this jagged pattern. And this is for the region k-means algorithm. For the scatter algorithm, we actually see something a bit more interesting. And this is where it might tie into the modifiable areal unit problem, because these multiple minima indicate potentially other spatial effects that are happening. And it would be interesting in the future to examine parameter estimates, because these may indicate scales at which certain processes operate. So we could be looking at a sort of analog to geographically weighted regression in that sense, in terms of discovering the scales of these processes.
3 minutes, Tyler, 3 minutes.
Wonderful. And then finally, this is the Ward clustering. And the Ward is the one that I'll present the actual spatial clustering of. And this one, again, has multiple minima, and you can sort of see there might be something interesting going on here. We haven't investigated that yet. The last thing I'd like to highlight on this slide is that these optimal clusterings, optimal according to the heuristic, the number of clusters are very similar between the three of them. So 16 for Ward, 14 for Scatter, and 8 for the region k-means model. And that's a very interesting thing. That it indicates some level of stability across the, in terms of algorithm choice in the heuristic. Although, of course, more work is probably required to determine that. Okay, and here is the optimal clustering for the Ward model. So on the left side, you see the original map of California's counties. And then on the right side, you see what the clustering produced when we ran it with the optimal number of clusters as determined by the heuristic. So interesting, pretty map in my opinion. So in the future, we'd like to challenge and weaken the assumptions of this heuristic, in particular the non-increasing one, because we think that has an interesting, the assumption on the model error, because we think that has an interesting connection to this multi-scale process idea, as well as examine parameter estimates at these multiple minima for the same reason. It would be interesting as well to substitute other regionalization methods, such as max P regions, thanks to a recent paper by Sergio Rey et al. In 2020. There is actually now a very efficient way to run the max P regions procedure, and it would be interesting to see how that changes things, if at all. As well as running perhaps just a spatial regression, spatial lag, spatial error model instead of a spatial interaction model. Because we do think this is a very general method. All you need is a model error in order to make the heuristic work. And finally, we'd like to incorporate other constraints into the optimization. So compactness or other things like that. They could come in the form of a constraint, which would be potentially, the more things we add to optimize, the harder it is to optimize any one of them, is the challenge that we're running up against. So that's all, and all from me.
Two questions for you in the chat from just say, would it be interesting to use bi-objective Pareto optimization for area fit instead of aggregating? Might make things more complicated, but might give you more.
Now, I'll be honest, I have no idea what bi-objective Pareto optimization is. So I can't really answer that question to its fullest. But yeah, I mean,
it's something to think about.
Yeah.
I suppose the Pareto optimization would consider, you know, the variables that you're rather than aggregating several variables together, to consider them as individual optimization functions that you're looking to minimize or maximize. So possibly something to look at beyond that. And then you did mention a link with geographically weighted regression.
Yeah.
And Juste also wants to know, is there some link with GWR with optimal bandwidth?
Absolutely. We definitely think there is a link to this, and especially in particular to multi-scale geographically weighted regression. And I think that that's like the next direction that we're going to take this project is to investigate that and examine how, if this could be like well, we want to see what happens when you just use GWR or MGWR as the spatial model here, but we also want to see how you can actually extract multi-scale processes from models using these aggregations. So it could sort of get it from either angle.
That's great, yeah. And just a final question, if there's nothing from the chat, just in terms of, say, for example, the scatter model, you showed a plot there of scatter at k equal to 14, I think. Have you thought about, or I'm sure you have, it's just you don't have a lot of time or pages on the paper. What's happening there between n equal to 30 and 45 is interesting. Have you thought about what kind of driving that?
No. So a little more information on these plots. We ran the clusterings a number of times and averaged all the results so that we could get smoother curves. And truth be told, we haven't really investigated this yet, and that's sort of again one of the directions that we're looking to take this in. But the fact that it lasted through these averaging is significant. That it's something that's more. It's not just noise. Yeah.
Yeah. No, it's a future work item rather than noise. So yeah, great stuff.